many semiconductor devices that we have seen, we, we either talk about the intrinsic charge carrier concentration, which is, for example, for silicon, that's 1.5 times 10 raised to the 10, or we dope it. When we say doping, we are adding carriers from those dopants, either N-type or P-type. But many semiconductor devices, they use charge carriers in excess of those, uh, which come from intrinsic or extrinsic uh, dopants. So the idea is that these excess carriers, they would add many more charge carriers into the system. They can come from shining a light. So we know from the black body experiment that where we said that, okay, if you excite it, we get light in quantized levels. So in the same way, if we shine a light of some wavelength, we can excite charge carriers within the semiconductor material. When that happens, we have many more numbers of charge carriers than maybe in that specified location where we are shining light. And that adds to what we call diffusion current. So in that localized region, the concentration would go up, and that's the diffusion current component in the overall current in semiconductor devices. Now, where do we inject these semiconductor materials depend on the device type or the combination. Is it a diode? Is it a transistor? Is it a photodiode? Now, you think about it, we use photodiode or photodetectors. It's nothing but exactly that thing, excess charge carriers. When that diode gets exposed to light, that light, those specific wavelengths in that light would cause excess charge carriers to be built up. When you have more charge carriers, the resistance of the device would go down, current would start flowing. So hence we see uh, motion detectors, we see in the garage sensor where you have two components. If you have done that, like all of us, we push the button of the garage. Before it closes, we jump the edge and get out, right? One way garage closing. So those things are, one side is sending a beam of light, the other side is sensing that light, and excess charge carriers are being produced. So this is chapter 4 where we will look at uh, the creation of excess charge carriers, especially by optical absorption. And what happens when uh, we have optical absorption, and what is the way how we calculate those things in the system. In a in a optical absorption experiment, many times we do that to look at the band gap energy of a semiconductor material, because there is a couple of conditions for that absorption to occur. Number one is the energy of the incident photon, like it is shown in this view graph A. That energy has to be bigger than the band gap of the material, right? So when you are projecting the light, the photons of the wavelengths, maybe we have white light where a bunch of wavelengths are going, or maybe we have monochromatic light where only one wavelength is going. But that wavelength, h mu as it is written here, that wavelength gives energy to that incident photon that has to be larger than the band gap, which is from here to here. So that has to be larger, so equal or larger. So we can add equal sign here as well. So I can say it has to be equal or larger. So it can barely get to the edge. If that happens, that photon will get absorbed by the material. But if wavelength of the incident light is smaller than band gap, it would just pass through. So for that wavelength, the semiconductor material would be act like it's transparent. There'll be no absorption. It will just pass through. Many times we deal with optical semiconductor materials and we want to design them to do something only when they are exposed to specific wavelength. But we also use this kind of system to, to find out the band gap of an unknown material for that matter. So this is in the idea behind the optical devices or excess charge carriers, that the band gap of the material is important because the incident photon would be absorbed only if the energy that's coming in is equal or more than the band gap. The photons that get absorbed will tell us what is the band gap. The photons that pass through will tell us, which just transmit through, will tell us that at least the energy is more than those. Now, once that happens, what we see here is an electron jumping from lower energy level to from valence band to going to conduction band. So this is for energy which is higher than band gap. So it ends up somewhere here. So we'll talk about B, but we're still looking at A. So in this process, what we have done is we have created an EHP, electron hole pair, right? Hence the excess charge carriers. So we have added electrons and holes by injecting light in it. And in B, then we say, okay, if it's at higher energy level, it has to bump, release energy and come to lower energy levels. So these energy states, which will be close to the conduction band, it will come back there and be stable for some time, because this excess charge carriers were created because we injected energy from outside. So after some time, it's gonna go back. That's the C part. When it goes back, what happens to the excess energy? Either that gets transmitted as wavelengths of very specific energy level, which is equal to Eg, or it may be, it's, or it may just give out as heat or the vibration of the material. So we have to look at A, B, and C separately to understand what's the process of when we say optical absorption. So they're very standard equipment that we use to do that, to do the whole process. And it involves a light emitter, monochromator, which is shown here. So we can emit a very specific wavelength. And this would result into creating extra charge carriers. It will create some current that will flow in that material, right? So excess charge carriers, current, they will be moving. Once that happens, they will, over some time, the current will die down over some distance, diffusion current. So what's shown here is, in this picture, is that the sample has some length, L, and we cause this I naught current, which is causing this current to flow over distance dx, and some of the, so we measure that current. What is that current? So we can use these values to exactly find out what is the light and what is the absorption coefficient. So that beam of intensity I naught falls on sample of thickness L. Oh, sorry, the I is intensity, not the current. The current is caused in the material where that the high the high concentration region will cause some charge carriers to flow to other parts, and that will be the diffusion current. Once this falls, it absorbs the photon which have lambda energy, and there is this intensity change over that small distance dx. So this is given minus sign to it because this is a decay. This is a degradation of that intensity of light that falls and passes through this distance. Now, alpha here is what we call absorption coefficient, a constant. When you solve this equation, we get a relationship which tells us that the change in the light intensity because of the absorption of the light occurs with this relationship. Now, there is IT which passes through and gets to the other side. And here then this X, we replace it with L. So then we can exactly find out what is the intensity of the light that did not get absorbed. Now alpha, the constant, changes with lambda and the material type. The alpha absorption coefficient changes with what is the wavelength and what kind of material is under investigation. But there is a relationship between alpha and lambda, which gives us good indication of what to expect on the change in the intensity. And we'll look at the plot in a slide later on. So the message here, we have a semiconductor material with specific band gap. We shine the light wavelength has to be greater than the band gap. If it is greater or equal, it will get absorbed. If it is not, it will just transmit through, and that can be used to find exactly what is the wavelength, what is the band gap of an unknown material. What do we call this phenomena? We call it luminescence. So there are many types of luminescence. So, but the luminescence, the basic definition is that it's the emission of light. Essentially, three steps that we saw before. A is the jump of electron to conduction band, what we call electron hole pair generation. And then when it gets excited by photon, it results after some time to come back. When it comes back from conduction band to valence band, it emits a photon. So it's light emission, which is because of the recombination of the excited carriers, right? So if we look back at this part C is what we call luminescence. This guy going back and in the process emitting a photon which has energy equal to the band gap energy, right? With me so far? All right, so, but what makes one type of luminescence different from another type of luminescence is how was this done? How were the electron excited? How did the EHP form, EHP generation took place? So that then makes one luminescence different from another luminescence. So there are 3, 4 types of luminescence that we would study, and one we will look more closely. Photoluminescence is where the part A, the EHP generation, happened because of a photon absorption, right? So we shined a light. The luminescence is if the original EHP generation, again part A, occurred because we had bombarded high energy electron on the material, which knocked off an electron from valence band and gave it enough energy to jump and go to the conduction band. Right? Or electroluminescence, which is that if the excitation occurred by applying a current to the sample, right? So they all are luminescence, but then how we created the EHP to start with would define it to be one type or the other. We use all of them in devices. We use all of them in semiconductor materials. So as designer, we have to know in one type of design what kind of excitation has to be used. Now, if you think about photoluminescence, again, going through the first line is just repeating what we have seen, I've shown you. That recombination process, so remember, generation is electron went to conduction band, and then it came to the lower level, and then that was called generation. When it comes back, falls to valence band, that process is called recombination. So this is a specific terminology we use to explain one from the other. Here we are calling this recombination to be direct recombination, which means that the electron is jumping directly to get down. It may not come directly. We'll look at those conditions also. But right now, this is a process which happens very quickly. So we shine the light, we will get a responding light coming out of the semiconductor material right away. The time of that process of recombination and giving out a photon is 10 raised to power minus 8 seconds. If you think about it, that's like a few nanoseconds, right? So 10 raised to power minus 9, if you put it, then tens of nanoseconds. Now, this means that as soon as you remove the excitation, the light that's coming out of the material will stop right away, because all the all of those photons coming out were because of the shining of the light. And within 10 raised to by minus 8 seconds, all of those excited electrons that were being generated were recombining so fast. So as soon as we remove the excitation, recombination stops right away. But if it does not stop right away, it continues for some more time, which means if the mean lifetime is a few seconds, that's the thing that we call as fluorescence. That's the material, or that's the phenomena we see in those, I don't know if you know, we put in kids' babies' room sometimes those fluorescing moon on their uh, on the ceiling. We put these uh, the light switch buttons that shine in darkness, or those they sell these. When good old days, we used to go for a fair or carnival. They sell these tubes filled with those some chemicals which glows in dark. Glow. That's luminescence. Sorry, that's fluorescence, which is a type of luminescence. The only difference is the mean lifetime of EHP is few seconds or even minutes or even hours, right? So today I've told you the process of why those things glow in the dark. Electron hole pairs formed, and it takes them much longer time to keep on recombining and keep on giving those photons, even if the re, even if the generation process has been stopped. Right. So we so phosphorescence, or now phosphorescence is if we use a phosphoric material, right? So it depends on the material that we're using, but overall we call them fluorescence. Now, when we talk about photoluminescence, the steps would be then that an incoming photon has HV1, we call that frequency V1 to differentiate it from the frequency of outcoming photon. It has to be greater than band gap. It creates an EHP. It goes to some higher level in conduction band, comes back. It may now, we talked about direct recombination before, but now C part is that before it gets to from conduction band to valence band directly, it may get trapped in some energy level within the band gap because we might have added some impurity into that. Remember, when we do N-type or P-type doping, there are extra energy levels that were generated. Depending on N-type, if it was N-type, there those extra energy levels were generated close to conduction band. And if they were P-type, those extra energy levels were generated close to the valence band inside the band gap. So in that case, then we call that impurity level having energy ET, trap, because it's trapping your electron that needs to come down. It stays trapped until we may have to thermally re-excite to it to go back to conduction band, and then it would jump directly to come down. So that would be electron falling directly back to the valence band. If it stayed trapped and then come directly, then come to valence band, then that's indirect recombination. But we're still talking about direct recombination. On the on uh, the physical, the optical absorption coefficient alpha, it has a relationship with the band gap, essentially lambda, because the energy lambda, we can calculate energy from that, from this relationship. It's given here, h mu equals eg, and if you put the mu equals lambda c in there, we get a way of relating lambda with, it's given here, with the energy of the material. And if it's direct recombination, that would be the band gap energy, like it's shown here in the picture. This is very important relationship because from this relationship, we can find energy or band gap energy of any material from the wavelength that it emits. So 1.24 is electron volts coming from these two constants, Planck's constant and speed of light, right? So this is energy units here. So how do we use this? So from the energy, from the wavelength that get absorbed, the lambda, and those that get transmitted through, that edge tells us what is the energy, the band gap energy of that material, of that unknown material. You have to know that energy and wavelengths are inversely related. So higher the lambda means lower the energy, and vice versa, right? I'm just putting this here like this because what that leads us is to exactly know, if I have to design a device for a specific wavelength, what material do I use for that? These are real materials. We know their band gaps. Knowing their band gaps tells the designer, tells you and me, what wavelengths is our target of our optical device, what material do we use. And from that knowledge that we can change the relative concentration and we can change the band gap, we can cover the whole range of this guy by changing different materials between their relative concentrations, right? So we remember we looked at plots of quaternary materials, gallium, aluminum, arsenide, phosphoric, and we can adjust their relative compositions, and that results in changing their band gap. If you can know exact band gap, we know exact wavelengths we are designing it for, right? Make sense? So far with me? All right. So excitation and photoluminescence, what we discussed before, it can either go directly from EC to EV, or it may get trapped and go back and forth and then go directly to EV, which would add to that extra time that we are talking about, that results into delayed emission, what we would call as phosphorescence or fluorescence. In case of electroluminescence, we know the example of LEDs, where the current from your battery basically causes injection of minority carriers into the crystal, where they recombine with majority carriers. So we give those minority carriers which recombine with the majority carriers, and recombination occurs, which gives out light. So this is what we do in LEDs. So electroluminescence is what's the cause of making that in case of LEDs. If we sum it up, you can have a wavelengths which gives 2 electron volts to an electron, so it jumps way up, but the after it gets through the process of recombination, it would give a wavelength which is at much smaller size. So what does that mean? It means that you can design a device that takes in many levels of incoming photons, but gives you back very specific wavelengths, monochromatic kind of a light source, right? So that can be achieved by the concept of photoluminescence. All right.